Hello, everybody. Today is our 8th lecture, and I want to remind everybody that today we have a homework assignment due. So I'm going to come around in a few minutes and pick up the homework assignment. But before I do that, and you will go ahead and get it ready for me to pick up, I'm going to write up where we were. So I'm going to tell you where we were. And where we were was that we had stated the completeness problem. So here's a recall. Okay. The completeness problem. It says the following. It says every non-empty subset of R that is bounded above has a supremum. Okay, so that's one thing that we had done last time, stated last time. I said that we can prove from that the following fact. Okay. We didn't prove it, but this is something that is true. It says that every, I might ask you to prove it for the next homework, non-empty subset of R that is bounded below has an infimum. Okay, so we can prove this fact based on the completeness property, which we assume to be an axiom. That's just something we're saying is true. And from this fact, we have something called Archimedean property, which I'll write on the board, and we'll go to prove that in just a second. So the Archimedean property and I think this is exactly where we left off last time. It says that if x is a real number, then there exists an n sub x element of the natural numbers such that x is less than or equal to n sub x. You can say less than or less than equal to. So our statement is less than or equal to. So we're both the same. So we're going to prove that in just a second. But if you don't mind, I'm going to take a second and come by and pick up the homeworks if you have them out. And I'll grade these and get them back to you on Monday, I think, with a chance to rewrite. And there's a strong possibility that I'll also have the second homework assignment ready. And it'll be due, after some time, but ready to hand out to you, okay? Thank you very much. Both of you. Okay, great. Okay, thank you. Now, remember what this Archimedean property was the same as. It's the same as the following. It's the same as the set of natural numbers is not bounded above. That's what this statement is telling us. And if you write down that the Archimedean property says the set of natural numbers is not bounded above, that is accurate. That is what it says. But it says it in these technical symbols listed above. Okay? But like I said, if you say this, that's correct with Archimedean property. Okay. So I would like to prove this, and it proves by contradiction. I'm going to do what's in the book here. So here we're going to let x, or suppose, I should say, suppose there exists an x element of R such that there doesn't exist an n sub x in n that's bigger than n. So that says such that for all, the contradiction of that, for all n elements of the natural numbers, n is less than x. That's what I'm writing. Remember, the Archimedean property says the set of natural numbers is not bounded above. Well, here I'm essentially saying, yes, it is. That for all natural numbers, there's this number out here that's bigger than this. Okay? Okay, so let's look at that. Well, if you remember what we'd be saying here is that, by definition, x is an upper bound for n. And by the completion property, what that says is then the soup of script n exists. It's a real number. Let's call it something. Let me call it u. So u is the supremum of script n, which I know exists because in our assumption we're saying that n, the set of natural numbers, is bounded above. And hopefully we'll get a contradiction. So I'm calling the supremum of n u. Okay. Well, in one of the lemmas that we've talked about for supremums, if you give me something just slightly smaller than the supremum, then it's not a supremum. Is that okay? It's not an upper bound. What does that mean? It's by one of the lemmas we just did. What does it mean? It means there exists something from the set we're talking about that's bigger than that guy, that's smaller than the supremum. So here, note u minus 1 is less than u. So u minus 1 is not an upper bound. Of script n. What does that mean? That means so there exists, let's say, an m element of natural numbers. So there exists some natural numbers such that u minus 1, since that's not an upper bound, there's some natural number bigger than it. If I add 1 to both sides, I have u is less than m plus 1. Now, since m is an element of natural numbers, then if you add 1 to m, you also get something that's in the natural numbers. Thus, u, remember what u was. U is equal to, what's u represent? It represents the supremum of the natural numbers in this setup. Okay? So what you have is u is not an upper bound for script n. But that's a contradiction. What does it contradict? U is the supremum of script n. Okay? So we've come to a logical contradiction, a statement that can't happen. U is the supremum, but here we're saying U isn't the upper bound. It's impossible. So we must have assumed something wrong. What we assumed is that there was some x that's bigger than every natural number. So for every x element of R, for each x in R, there must be something in the set of natural numbers, I call it n sub x, such that x is less than or equal to n sub x. And that's the proof. What's the proof by contradiction? Before I go on, let me give everybody a chance to look at it, see if they want to ask anything about it. You're more than welcome to ask something. Get in. Anybody have any questions about what we did? Anybody with any questions? Well, if you happen to come up with questions later, don't hesitate to ask. It's okay. If you're looking back over it, reading over your notes, learning this proof, you say, wait a minute, how come this is true? How come this follows? Concentrating more on it at some point, and you want to ask about it, please feel free to come by and ask. Okay. Well, now we're going to talk about some corollaries from the Archimedean property. This Archimedean property is a statement that we're going to use a lot. The fact that the set of natural numbers is not bounded above, it's going to be something we use throughout this class, especially dealing with sequences, okay? Which is a topic that will be coming up soon. Okay, now let's look at some corollaries to the Archimedean property. So I'm going to list these straight out of the text. But here's the corollary. It says, if we're looking at script S, defined to be the set containing all numbers of the form 1 over n, such that, as well, right? The colon here means such that. Okay, this colon means such that n is an element of the natural numbers. Then the infimum of script S equals to 0. Okay, so before I prove this, let's note just what script S is. What does it mean to contain numbers of the form 1 over n where n is a natural number? Well, if you take a look at the first natural number, you have 1 over 1. What else is in there? 1 over 2, 1 over 3, 1 over 4, and so forth forever. Okay? So that's what's here. Okay, so we're ready to prove this. We're going to let script S be equal to the set that contains 1 over n, those types of numbers, such that n is an element of the natural numbers. We want to show the infimum of script S is 0. How are we going to show the infimum of script S is 0? Well, first of all, we don't even know the infimum exists. So we got to establish that. Okay? And then secondly, once we establish that the infimum exists, we got to show that it's equal to 0. Okay. Well, here's the way that we're going to do this. So first of all, note that everything in S, that's the form 1 over n, that's going to be greater than 0. That's true for all n element natural numbers. So you give me a natural number, 1 over it, I'm saying it's positive. Okay. Why is that? Well, here's the reason it's true. If you give me a natural number, the natural number isn't 0. Okay. So its multiplicative inverse exists. And every natural number we proved was greater than 0. And so when you take n, which is greater than 0, times 1 over n, you get 1. Okay? So here, if 1 over n was not greater than 0, you would end up getting that 1 would be less than 0. That's what the argument is. We've done it for like 1/2 arguments for that. Same argument, except it's 1 over n. So instead of 1 over 2, 1 over n. So this is the natural number. So look. So for each element in script S, what do I know about each element in script S? Well, it looks like 1 over n. It's greater than 0. So what does that say about 0 for script S? It's a lower bound. Okay, so 0 is a lower bound in script S. Okay. Now, one of the things that I recalled today was the completeness problem, and then a fact from it. And the fact from it, if you give me a non-empty subset of R, and S is, because there are natural numbers, so 1 over natural numbers, there are those types of numbers, so that means S has got things in it. If you give me a non-empty subset of R that's bounded below, that means it's blank exists. What's blank? And infimum exists. So the infimum of S exists. Since 0 is a lower bound, then how does the lower bound compare to the infimum? What does infimum mean? It's the greatest lower bound. So if 0 is a lower bound, the infimum has to be not less than it, not less than 0. Greater than, because it's bigger than all lower bounds. So, it says that the infimum, that 0 is less than or equal to the infimum of script S. Just for notation sake, let's let W, that's what the book uses, equal to the infimum of S. So what we're saying here is that W is bigger than 0. Okay. But what I want to do is we want to show that W is equal to 0. That was the conclusion of the theorem, or corollary. Okay. Well, here's the way we can do this. And I might have to repair this. If you give me a second. We're good so far. But if you'll give me a second, here's what I'm going to do. Here, I'm going to say let epsilon be greater than 0. So we're talking about any positive number you get. Then, by the Archimedean property, well, here's what I want to do. Then, instead of Archimedean, let's say this. Then, 1 over epsilon is greater than 0. So, by the Archimedean property, I'm giving you a number, okay, 1 over epsilon. What's the Archimedean property say? It says 1 over epsilon is not an upper bound for the set of natural numbers. That means there's a natural number bigger than it. Is that okay? So that means, so there exists, I'll say an n element of the natural numbers such that n is bigger than 1 over epsilon, bigger than or equal to.
So that means that 1 over n is going to be less than or equal to epsilon. Now, what do you know about w's, the infimum of script s? Well, 1 over n is in script s. So what do you know about w in comparison to 1 over n? That's right. W is going to be less than or equal to 1 over n, which is less than or equal to epsilon. And of course, w we found out is greater than or equal to 0. Is that okay? So we got this in the column. So here's what we have exactly. 0 is less than or equal to w. And here I can make this strictly less than if I wanted to, but and I will. You can make this strictly less than, which I'll say is less than epsilon for all epsilon. Make less than for all epsilon greater than 0. There was a fact that we said, if you take a look at a number that's less than or equal to every positive number, then that number had to be, say it again, please. No, it's got to be bigger than or equal to 0, but it's less than or equal to every positive number. So it's got to be 0. That's what it has to be. And remember what W is, it's the infimum of S, and that's what we're trying to show is equal to 0. Okay. You know, when I said here, I would like to make an adjustment. Here, I'm going to pick an n bigger than 1 over epsilon. So this happens. So I'm going to change this to this every time. And that makes it match our theorem perfectly. And look, if I can get one natural number bigger than or equal to 1 over epsilon, then you get one natural number even more bigger than this by taking n plus 1. Because if n is a natural number, then so is n plus 1. And if n was greater than or equal to 1 over epsilon, then n plus 1 is definitely going to be greater than. Is that okay? That's how come I can just pick an n that's greater than. I mean, I know there's an n greater than or equal to 1 over epsilon. So that means there's an n that's greater than it, because I just go n plus 1. Okay, so that's a corollary. There's another corollary I'd like to look at, and that's corollary to the Archimedean property, because we used the Archimedean property to get it right here. Here's what it says. It says, if t is greater than 0, there exists an n sub t element of the natural numbers such that 0 is less than 1 over n sub t, which is less than t. We won't prove that. What's that saying? Hey, if you give me some positive number, that's what this corollary is saying, then there's some natural number out there that's less than, that 1 over that natural number is less than the positive number you gave me. That's what it's saying. That's in part what it's saying, that's the main thing. Here's the proof. We'll let t be greater than 0. And really this is based on the corollary we just had. Thus, t is an upper bound, is not a lower bound to script s equaling to 1 over n such that n is an element of natural numbers. Why is this? Well, the reason this is true is as the n, by what we just showed, of strict S. What was that equal to? What was the n for this S? We just did it. Say it again. 0. So the greatest lower bound for this set, the biggest thing that's the lower bound for this set is 0. So if you give me something bigger than 0, it can't be a blank for this set. Yeah, can't be a lower bound. Is that okay? The greatest lower bound for it is 0. It's the biggest thing that's the lower bound is 0. So you give me something bigger than 0, it can't be a lower bound. So what does that mean? What does it mean not to be a lower bound? Well, it means that there exists something in here that's bigger than t. Is that okay? I'm sorry. If it's not a lower bound, there exists something in here less than t. That's what I should say. So there exists a 1 over n sub t that's less than t, where n sub t is an element of the natural numbers. Let me go a little slower. Look, what I'm claiming is t is not a lower bound. What does it mean to be a lower bound? To be a lower bound means you're smaller than everything in the set. Smaller than everything. But that's not what's happening. So t is not less than or equal to everything in the set. So there's got to be in something in the set that's smaller than it. I'm calling that 1 over n sub t. That's what's in this set. It's smaller than this guy. Okay? And to be in that set, what the bottom has to be a natural number. Okay? That's what I have. Now, thus, we can say, you know, if you're in 1 over n sub t is in S. So here's what I have. We have, well, 1 over n sub t is 1 over a natural number. And we know that natural numbers are positive, so 1 over this guy is going to be what kind of number? Positive. So that means 0 is less than 1 over n sub t, which is less than t. And that's what I wanted to show. I want to do another corollary to the Archimedean property. Did I do this on the board? Did I turn the camera for this? I don't know that I did. I don't know that I did. So if I didn't, there's the material. Let me give everybody a second to write that down. So, I want to do one more corollary, but before I get to that corollary, there's a fact that I'm just going to state. It's called the well-ordering property for the set of natural numbers. Let me get it word for word on the board from our text. And here's what it says. So this is a big fact. Here's what it says. It's a well-ordering property of natural numbers, so it's stripped in. Here's what it says. It says every non-empty subset of the natural numbers has, and by the word has, I mean contains, a least element that's something that we're going to assume is a true statement. What we mean by this is if you give me any collection that's non-empty of natural numbers, any collection of natural numbers that's non-empty. Let's say we have 17, 3, 47, 1,327,576. Okay.
It has a least element. It contains the smallest number. What's its smallest number?
3 is this set's least element. Look, the point of emphasis here, if you're a subset of the natural numbers, you're bounded below. So the infimum exists, okay? It isn't that it's got an infimum, it's got a smallest element. It's that it contains its smallest element. Not only is the smallest element out there, but it's inside the set. And the infimum doesn't have to be, it's in the set, the smallest element. The infimum does not have to be in every set, okay? Even if it exists. But for non-empty subsets of n, it does. All right, let me write up one more corollary. The Archimedes problem. Okay, so I'd like to use the book's proof for this. So give me a second. Here's what it says. It says, if y is greater than 0, there exists an n sub y on the natural numbers such that n sub y minus 1 is less than or equal to y, which is less than or equal to n sub y. I'm going to write down this way. I'm going to change the corollary. I'm going to write to that. I'm going to take a lesson. Yes. Yes. Thank you very much. I need to turn. Thank you all. After I need to turn. Okay. Oops. Thank you very much. Okay, first of all, I've changed the corollary from what it was in the book to this. What was in the book was fine. I'm going to write something a little bit more exact. What is it that I'm saying, or that the book is saying in this corollary? It says, if you give me some positive number, okay, there's a natural number out there such that that natural number is slightly bigger than that number, and if you subtract 1 from it, that natural number, you're going to be less than or equal to that positive number. Okay, you give me a positive number. Essentially, what I'm saying is, if you give me a positive number, it's sandwiched between 2 natural numbers, or it's sandwiched between 1 and 0. Is that okay? So here, this is what I'm thinking. Here's the number line. Here's 0. Here's 1. Here's 2. Here's 3. Here's 4. And so on. 5. It goes on forever. Let's take something positive. What if it was right here? What if it's right there? Can you give me a natural number such that that natural number is bigger than, this is y. Can you give me a natural number that's bigger than y such that 1 minus that natural number is less than or equal to y? What would it be? What would your natural number be? What's the natural number out there that's bigger than this guy, but yet 1 minus that natural number is less than or equal to that guy? Come on, this is easy. 1. You give me 1. 1's bigger than the number I gave you. And if you take 1 from 1, you get 0, and 0 is bigger than it. Okay. What if I gave you 1? What if y was 1? What's the natural number that's bigger than 1, but yet 1 minus that natural number I'm giving you, that natural number minus 1 is what I should say, is less than or equal to y. Y is 1 in this case. Yeah, go ahead, Adam.
Still.
2. You take 2. 2 is bigger than y, and if you take 2 minus 1, you get 1. And that's bigger than or equal to y. Is that okay? And every positive number is going to fall into that category. Is that okay with everybody? That's the way that you can sandwich any positive number between a natural number and 1 less than it in this manner. Okay, okay, let's look at the proof. I'm going to need a little help with these proofs, so I'm going to use the book. Today I need to use the book. Okay, so first of all, let's consider this set. Consider the set E sub y consisting of all m element of the natural numbers such that y is less than or equal to m. So let's look at this.
Is that what that means, consisting of, or is that equal to?
It's equal to. It's defined by this. And I should have equal to. Okay, so we're looking at all natural numbers that are bigger than 1. Okay, the first thing I want to tell you about this set is, how do I know anything is in the set? What is this set? This consists of all natural numbers that are bigger than 1. How do I know that there's a natural number that's bigger than 1? Wait just a second, think about it. I'm giving you this number y. How do I know there's a natural number bigger than it? What tells me that? What fact tells me it? Mm-mm. Mm-mm. Don't let my unknowns bother anybody. Okay? Think back.
That the set of natural numbers isn't bounded above.
That's what it is. If there wasn't any natural numbers bigger than y, then y would be an upper bound. But that can't be the case. The set of natural numbers isn't bounded above, so I'll give you y. There's a natural number bigger than it. Is that okay? And so by the Archimedean property, thank you very much. E sub y is non-empty. Okay? Okay, so there's something in it. And now I'm erasing what I'm going to use next. So E sub y is a non-empty subset of natural numbers. Of natural numbers. Okay. So what does that mean? By the well-ordering property, it contains its least element. Is that okay? Of n, E sub y contains its least element. Let's say n sub y. That's why I'm calling it its least element. Okay. Now, since n sub y is an element of E sub y, what things do we know? N sub y is a natural number, because that's what it means to be an E sub y. But what else does it mean to be an E sub y? So look back at the definition of E sub y. Got to be a natural number. And what else, other property do you have? You're bigger than y. And that's what I want to emphasize. Is that okay with everybody? Okay. All right, now, we still have one more thing to show. We've got to show that n sub y minus 1 is, I'm erasing it. I've erased it. Is less than or equal to y. That's right, now. That's what it said. This was part, what's written there on the board, the last thing, that's part of what we want to show. We must show n sub y minus 1 is less than or equal to y. That's still what it's left to show. If we do that, we've got the theorem. Or got the formula down. Okay, so I haven't shown this. That's what I got to show. Okay, I'd like to break this up into cases. So here, we will consider two cases. So, case 1. Y is an element of 0 to 1, open interval like this. So y is something in between 0 and 1. First of all, let us note since n sub y minus 1 is less than n sub y, and n sub y is the least element of e sub y, then n sub y minus 1, I'm just going to wait if everybody's saying, what the heck am I going with this? Here's what I'm thinking. N sub y is the smallest thing in e sub y. I'm giving you n sub y minus 1. What can you tell me about it? I can tell you one thing, it's not in e sub y. Because anything less than n sub y is not in e sub y. So it's not in e sub y. You know, I might move my case here just a second. Okay? Matter of fact, I think I will. What does it mean for n sub y minus 1 not to be in e sub y? Well, what did it mean to be in e sub y? E sub y members had two qualities. They were natural numbers and they were bigger than y. That's what it is. So at least one of those fails. Is that okay? Okay. So, so at least one of those fails. So either n sub y minus 1 is less than or equal to y, or n sub y minus 1 is not a member of the natural numbers. You know, I don't think I have to have this case 1. I don't think this is what I need. I think I'm going about it fine. I think I'm going to erase this in a second. I'm sorry. Okay, if n sub y minus 1 is less than or equal to y, then the statement is true. That is, we have n sub y minus 1 less than or equal to y is less than or equal to n sub y. Not just less than. And we're done. Okay? If n sub y minus 1 is not an element of the natural numbers, okay? then n sub y minus 1 had to be what number? So, okay, think about this for a second. Let me get out of the way. Look, n sub y is a natural number. What natural number is out there so that when you subtract 1 from it, you're not a natural number? There's only one natural number that you subtract 1 from, and you're not a natural number. If I give you 37, when you subtract 1 from it, you get 36. That's a natural number. What's the only natural number out there that when you subtract 1 from it, you don't get a natural number? Say it again, Chuck.
1.
1. 1 minus 1 is 0. 0 is not a natural number. So what is that? N sub y must have been 1. So what's n sub y minus 1? 0. Since here, remember we were talking about y. What property did we have about y? There was only one thing in the statement about y. Now that was in the definition of E sub y. In the statement of the theorem, the corollary, there was only one thing we said about y. Y was greater than 0. Since by assumption, y is greater than 0, we have, in this case, that 0 is less than or equal to n sub y minus, is less than or equal to y, is less than or equal to n sub y, or n sub y minus 1, which is what 0 is less than or equal to y, is less than n sub y. That's what I'm going to write. Okay, and that concludes it. So in all cases, there exists an n sub y such that n sub y minus 1 is less than or equal to y, which is less than n sub y. That's the case. But I need to go back and adjust something. So there were two cases. You just talked about n sub y minus 1, whether it was in the set of natural numbers or not. So here, when I said there were two cases, that was true. But the two cases developed not because of where y was, but rather why n sub y minus 1 wasn't in the set E sub y. Okay? Either it's less than or equal to y and we're done, or it's not a natural number. And still, even if it's not a natural number, we're done. It will work. Okay? So that ends the proof. So let me come back here. So I had to make that change. I just had to take away that case. We didn't do it that way. Okay? Okay. All right. I've got just a few more minutes. Okay? Not 2 more minutes, and then I'll be done. I want to give a definition and fact, and that's what we'll start with next time. Is proving this fact. But here's the definition. A subset, script S, of R is said to be dense in R if for any two real numbers x and y, with x being less than y, then there exists an S, element of script S, such that x is less than S is less than y. I'm going to stop. That's what we're going to finish with, but I'm going to explain this a little bit more. That is where we're going to stop. I'll do the theorem next time. But I won't explain this. At least how I think about it. Okay. We're using this word, dense. That's what we're defining, dense. You might have heard this word before. Okay. Dense. Sometimes people say,
Boy, this is a insult. Someone says that another person is dense, they mean that they're not smart. Really, the way that that can be interpreted is they're thick-headed. Okay? Another way of thinking of dense, or a part where you've seen dense maybe before, is when we talk about population density. And so if we say the population is dense in this city, what's that mean? It means there's a lot of people. It means everywhere you look, there's people. It's in that sense that we mean dense in this mathematical definition. It's that everywhere you look, there's some guys from this set. So this subset S is dense in all, meaning that set S has members everywhere. What do we mean? What's more a refined definition to capture that idea? To be dense. If you give me one real number and another real number, they aren't the same, one was bigger than the other. If script S is dense, no matter what two real numbers you gave me, that's got a little gap between them, there's a member from that set in between that gap. Does that make sense to everybody? So when you look at the real line, to be dense in the real line, that subset has members everywhere. It's just everywhere. You can't find a spot, a little gap along the real line where there isn't a member from S. That's what it means. That's what this is saying. And what we're going to have is a theorem. The next thing I'm going to write up is called the density theorem. And what it says is that the rational numbers are dense in all. The rational numbers are everywhere. You can't find a gap on the real number line where there isn't a rational number. And we're going to prove that. Stay and prove it next time. Thank you very much for your time and patience.